Now we will be solving this question. So they have given the height which is like 20 meter, and similarly the shaft power is 11,772 kilowatt, and they have given the outer diameter of the runner and the hook diameter as 1.75, and the guide plate angle which is like the alpha, which could be represented here. The alpha is also given, and other is hydraulic efficiency is given as 88%, and they have also given the overall efficiency which is 84%. And in the question they have mentioned that the wire velocity at the outlet part is 0. So therefore when you draw this when you try to draw this figure, you can draw it in such a way that the inlet part of the moving plate will be similar to what we have studied, but for like the outlet part it will be in this way. Now we will be solving the question. We are supposed to find out the runner vane angle at the inlet as well as the outlet, which means it will for the Kaplan turbine the angle will be so, which can be, if you want to determine the runner vane angle, that is possible. It can be determined using a tan theta, right? So which means we will be Vf1 divided by Vw1 minus U1. However, we don't have value for we don't have the value of Vf1, we don't know the value of Vw1 and even U1. So therefore we have to start from the information that we. So for that, let's start with the first thing is the overall efficiency. We don't know the value, so we will start from the known value, that is we know the formula for overall efficiency, and they have given the overall efficiency as well, which is overall efficiency is the power of the shaft divided by the work power that is delivered by the water to the runner. So, and the first thing is we will start from the work, that is the power that is delivered to the runner. It can be determined using density, G, Q and H, and I remember mentioning it in the class. So, and since in our case the shaft power is given in case of kilowatt, so therefore let's try to divide this with 1000, so we will be getting in kilowatt as well. From here, if we just try to substitute the value, then by substituting the work power as shown in this figure, then we will be getting overall efficiency is taken as 0.84. So from there we know that the shaft power is 1772 kilowatt, and the work power is, we know that is 1000 times 9.81, and we don't know the discharge, but we have some idea about the height. We already know the height, it's given as 20, right? So by using this information and divide it with 1000, so from here you will get the value of discharge as 71.428 meter cube per second. This will be our discharge. So if we know the discharge, then we have one formula. Just let's go to this equation, and we have formula. Note that the area can be determined using this. So let's write this formula. If you want to determine the discharge, it's area times flow. So therefore we will get it by 4 naught square minus dB square times Vf1. And if you substitute all the known values, let's substitute, that is discharge 71.428 meter cube per second, and we know pi by 4, and we also know the outside diameter, which is 3.5. It's given in the question, and even for this hoop it's given in the question. So from there we will be determining the Vf1. So if we solve this, we will be getting the Vf1 as 9.9 meter per second. So after getting this, so let's move to the next one, that is from the inlet velocity triangle. We know that tan alpha will be Vf2 divided by Vw1, right? So So the only unknown value is VW1, so take the VF2 divided by 10 pi. So from here you can, we got it as 9.9 VF2. So in case of Kaplan turbine, VF1 will be equal to VF2 and U1 will be equal to U2, that is plate velocity and the flow velocity will be same. So therefore we can take it as 9.9 divided by 1035, and the angle 35 is already given in the question, so we will be getting it as 14.14 meter per second. So after getting this value, then we have got almost all the value. Then try to substitute in case of hydraulic efficiency. That is, we know that it is VW1 U1 divided by GH. So here we know the hydraulic efficiency is 0.88, which is given in the question, and we got it as 14.14 times, we don't know the value U1, then divided by 9.81 times 20. From here you will get the value of U1 as 12.21 meter per second. After getting all this value, then we can determine the run and wane angles, that is tan theta equal to VF1 divided by VW1 minus U1. So just substitute it, it is 9.9 divided by 14.14 minus 12.21, so we will get it as 5.13. And just to take out this theta aside, tan inverse of 5.13, you will get it as 78.7 degree. And since U1 will be equal to U2 in case of Kaplan turbine, that means it is 12.21 meter per second. VF1 equal to VF2, it is 9.9. We already used this. After getting this value, then we can determine the outward velocity triangle, that is, just use the figure that velocity triangle for moving jet that I have drawn in the above section. So you will get to know how we are using this formula and all. This we will be moving to the part 2, that is speed of turbine. You will be used to in case of Kaplan turbine, which is pi d and divided by 60. So from here we will know the speed, that means speed will be 66.63 RPM. And that's so. With this we are coming to the end of the chapter number 7, and there is one more thing in the PPT, that is about the importance of draft tube. You can once go through, and thank you.